So I do have one for mass moments of inertia. It's a little bit more of like a 3D problem. So in that way, it might be a little bit more tricky than what you've seen before. So we'll do just one of those and then a rigid body kinetics problem to review from last class. So since there has already been so much coverage of mass moments of inertia, I think I'm going to mostly leave this one to you. This problem, the Hibbler book always does like silly stuff to try to make it harder for you to find the mass instead of just telling you the mass. So in this one, remember in other ones that are like 2D problems, they sometimes give you a mass per unit area. And you have to find the area and then multiply by that factor to get the mass. Well, this one gives you a density because it's a three-dimensional shape. So you first have to find the volume of each of like the three components that make up this composite body, and then multiply by the density. But I thought that was kind of silly, so I'd rather you just focus on the finding the mass moments of inertia. So masses are here for you. You can assume they're correct if you trust me. And then I'm going to leave you there. So these should be the only two reference items that you need. So that's it. Yeah, let me try. Oh, my nemesis.
It's just hard to see the equation.
Oh, I know. All right. Instead of zooming there, or see if I can do it here.
Are we gonna have any of these equations are they in the formula sheet?
They're not currently on your formula sheet, but if I ask you a question that requires them, I will give you the ones that you require.
Like for all of them or just the non-basic ones?
I will give you whichever of these you need for the problem that I give you. For the standard shapes.
Correct, for standard shapes.
Right, like rectangular prism. Actually, for whatever reason, I don't know why, but the rectangular prism is not in the Hibbler sheet, but I found it online, and so I would give you that. The cylinder is on the Hibbler sheet. It's in like one of the covers of the actual textbook. So whichever ones of those you need, I will give to you. Maybe it's under advanced sharing options. Nope. About that. Better?
Yeah.
Can everyone online hear me?
Yeah, we can hear you.
Great, thanks, David. We lost?
No, the drawing part is just killing.
Yeah, it's just
Yeah.
it's like the whole reason I switched to an iPad for this class. So tired of drawing hand notes and like you show like the drawing on the board and like try to draw it.
And I move too fast.
Since you move too fast, the time too slow.
Well, so remember that I post these. I do post the PDF afterwards. So if you want to just not draw it and just refer back to the picture, you can. That's also true.
You know, like weird, just like
Funny people
taking
do it.
pictures of yeah.
I don't care. I have seen much stranger.
That's the mass for each cylinder?
Yes, each one individually. How many of you have started homework 6?
So we'll do Thursday, right?
Yeah.
I just turned it on last night.
Oh, wow, early.
Well, I started it, I was like, this is actually not as bad as I thought.
The mass moments of inertia is one.
Last one was a little challenging.
I was gonna say, how'd you do with the last one?
It took me, it took me a minute to figure it
Well,
out.
did you
Okay.
And
did
it's
you
weird.
look up the equation for it, or did you give it to us?
For the central,
I
I
didn't
looked it
give
up.
That's right, what?
The
This-
cell-
The mass moment of inertia, or not the mass moment, you could look up the center of gravity, that was fine.
Yeah, that's what I.
How did you find the mass moment of inertia for the half cylinder though?
So you relate the center of it to the middle, and then you relate the middle to the bottom.
Yeah, but it's not in any of your sheets for like the center of it.
Then maybe I did it wrong.
You only have a full cylinder in your
So-
sheets. No, well, kind of, like
What
you,
do mean that, you mean like how to find the center of it?
the mass moment of inertia about an axis that goes through the center of a semicircle.
But it's not through the center, it's through the bottom.
It's asking you about the bottom, but you have to know about the center to find about the bottom.
Right.
Yeah, but you don't have about the center either. And I mean, you could probably find it online.
Yeah, I think I just looked up the
Just
equation.
look up the equation, yeah.
Yeah,
Then-
because it was
Okay.
like some crazy equation, it was like 1/4 minus like.
Yeah.
16/9 pi squared, something like that.
That's fine, I'll accept it, but you could have rederived it by doing parallel axis theorem for you could have treated a full cylinder as a combination of two half cylinders and backed out the equation for a half cylinder.
Can.
Do you want me to do it?
Yeah, that sounds.
I'm gonna post the solution guide to that. Don't you want to do a new one so you get both?
Sure.
Sarah Beth, I think I still have your exam. Okay.
You do. I'm gonna have to come by your office hours to get it.
Okay, no problem. Come by whenever.
Like, I would just like, find the moment of whatever. And so conceptually.
Yeah.
What I'm trying to do.
Yeah.
Is take the cylinder, find its distance from the x-axis and its mass, and like. I don't really know what I'm doing, I guess, now that I think about it.
Can you just do parallel axis theorem for?
That's what I'm thinking,
Like you do the,
find the moment of inertia about x double prime. and
yeah,
then do parallel
and then you
axis
do it to x prime.
Yeah, so let's,
theorem.
I can walk through my game plan. So it's asking you about X prime. But it's actually best to use X as a waypoint because X is the center of gravity of the whole body, or X goes through the center of gravity of the whole body. So you can do this in two steps. So the first is to find IX whole body, which goes through the center of mass of the whole body. And then two, in a second step, use parallel axis theorem for the whole body to find IX primed. With parallel axis theorem for whole body. So if your first step is to find IX whole body, we know that this is the sum of inertias of each of the three objects about IX.
Can you scroll down, please?
Yes,
What's the we do?
whole body. Cylinder one plus IX cylinder two plus IX plate. Or whatever you want to call the rectangular thing. So some of these will require parallel axis theorem. Okay, so take it as an indicator that maybe you need to study how to figure out this game plan.
Just scroll up one more time.
Yep, no problem.
Parallel axis theorem on the equation sheet.
I'm not sure. To be honest, it probably shouldn't be. That one's like so easy to memorize. It's just IP equals IG plus MR squared.
I thought it was minus or plus AB squared. Is that the same thing? Oh,
IP equals IG plus MR.
centroid, okay.
Centroids are area based. Mass moments are mass based.
Yeah, she like mass, parallel axis, got that one. She listed the equation.
I'm sorry.
No, it's okay, I was like.
So yeah, okay. So you use parallel axis theorem for areas as well. Got it. So is that IP equals IG plus AR squared?
Yeah, she's D though, but R and D.
A D, yeah, R, okay, got it. Centroids.
Like if you're trying to.
Like if you got like a cross beam, you solve for like
Your area moment.
Yeah, we took it last year too.
You use it in bending.
The bending.
It's bending, yeah.
It's bending.
I was taught it.
Negative MY over I or something like that.
Yeah.
Yeah,
Okay, so tell me, which of these do we need to use parallel axis theorem for?
So
The two cylinders, yeah. The plate, that x-axis already goes through the center of mass of the plate, so that one we should just be able to read off the sheet. So the next step I usually like to do, I kind of belabor this a little bit in that I do an entire step of just filling in the variables for parallel axis theorem here. So I'll use square brackets to keep everything organized into the same 3 chunks. So I do yeah, I can't either. Okay, so for cylinder 1, the center of gravity goes through X double primed. Okay, so I have I X double primed plus M cylinder 1 R, the distance between X double primed and X squared, and this is for cylinder 1. And then I need to figure out what is the axis going through the center of mass of cylinder 2. That's X prime that I doodled all over. Okay, so X primed. Cylinder 2 plus IX of the plate, which we need to read off of our equation sheet. So with the rectangular prism, what you want to notice is that for each of these equations, the 2 lengths that are on the right-hand side, those are the lengths that form the face that the axis pierces. So for instance, with the B axis, I pierce this face here, which is made up of B and C. So if I look at the B axis equation, the variables on the right are B and C. Okay. So if I am looking at our plate and I want to know what is the moment of inertia about this X axis pierces the face that's like right here on this like profile image or frontal image, depending on, I don't know, it's a crank. It doesn't have body planes like a human does. Okay, so this face is made up of the 0.3 meters or 0.03 meters and the 0.18 meters. Okay. So that means that down here, it should be 1/12 M plate 0.03 squared plus 0.18 squared.
For these questions, do you want us to always put it in like kilograms and meters?
The main reason I do that is because if you were to solve here, that's in meters. Of course, I did that for you. Meters are better. But what we're gonna find, I think, is that we get a really, really tiny number, which is, it's fine. As long as you get it right. Okay, and then it's just plug and chug. So what is I x double prime for cylinder one? Whoops. Very good. What is the radius? 0.01, because it's 20 millimeters.
Oh, I was looking at the bottom. Which.
That one
I
is
was
also
looking at
20
the- I
millimeters.
was looking at the other picture.
Okay,
Yeah.
got it. Okay, so 1/2 M cylinder one 0.01 squared. Plus. And then what is the distance between X double primed axis and X?
60.
Yep, because it's over here, we see that the first cylinder, the center of the first cylinder is 30 millimeters from the top. This whole distance is 90 minus the first 30 is 60 millimeters, so 0.06 meters. Okay. What we're gonna find is that everything is actually exactly the same for cylinder two because the same thing is symmetric and the two cylinders are the same size. Okay, so I am just gonna put a 2 out here and we'll ignore cylinder two. And then really we have just masses to plug in after this, so. So cylinder one, 0.123. And the plate is 0.8478. Know what you get.
Or the blue thing, that's it.
Sorry?
Or, 325.
Yep. Very good. So 0.00325 or You really like scientific notation. It's 10 to the third. Okay, but that's still not what the problem asked us for, right? We had a two-step game plan and we only executed the first step. So now we need to find I about x primed for the whole body using parallel axis theorem. So what'd you get, Micah?
719.
Very good.
It's two.
You got 1.0938.
For the total mass.
Why is mine off there? But it's got 1944. Like, how am I doing that wrong?
Did you round the decimal, any of these decimals?
Missing three.
Okay.
Why in books sometimes they use slug when like it's. So I was looking at some of I was going through some of the questions and it had like slug, like it's like slug feet squared.
I think that's what they call pounds mass.
Okay.
I think it's just a different,
Slug is pounds. It's just why slug? Metric's just better. Metric's just better.
it is, that's true.
Like for at work they use periods and time. But I learned to like it because I started being able to like approximate my sizes for my designs in material.
You got it in your head, yeah.
And then I have a 3D printer now and I'm doing this project, and 3D printing I found works better in metric, at least for my situation. There's one of the guys in my mechatronics class who was ready to die for the fact that I'm wrong. I didn't know our conversation was gonna get so heated. I was like, whoa.
I've never heard anyone actually argue for imperial units.
Well, he was just like, you should be able to use anything in 3D print with the same accuracy. I'm like, I realized I was getting printarius, so I switched my whole project to metric. But it's still like, I'll like be designing something and I'll like go to approximate the size and I'm like, I have no idea how long this is.
Yeah.
So it's like, yeah, 100 millimeters, and it's like way too short.
Okay, alrighty, let's do a kinetics problem here. We've got a motorcycle going up an incline. The motorcycle and rider have a total mass of 900 kilograms and mass center at G, which is really dark in this image. So G is right here. If it is traveling up the slope with a constant acceleration of 3 meters per second squared, determine the normal reactions on the front and rear wheels. Also, what is the required friction force developed on the rear wheel? The front wheel is free to roll. Okay, so here's why I don't really like problems with wheels in this book. We've talked about roll without slip, right? You have to have some friction in order to roll without slip. Now, that's going to be static friction because the point that's in contact with the ground is not moving relative to the ground. That's the definition of roll without slip. And the only reason we're able to do that is because there's friction between the wheel and the ground. Okay. However, in these kinetic problems with like bicycles and motorcycles and things with wheels, if they tell you what is the required friction developed on the rear wheel, but they tell you that a different wheel is, quote, free to roll, they're saying put a friction force at the rear wheel, but do not put a friction force at the front wheel. And I don't quite understand the logic behind that because there is still friction for freely rolling without slip. Maybe it's a misunderstanding on my own part, but this is the way to interpret the way they word these problems in the book. Okay. So they're saying these two things for a reason. And the reason is that in your free body diagram, they want a friction force at the rear wheel and not at the front wheel. So what should I write down for my known? I think that's a good idea. I think that's a good idea as well. When things are constant, I like to mark that they're constant just in case that matters at any point. Because usually it means like a derivative beyond that is 0. So I try to call that out whether I need it or not. I usually find that important. And then I'm gonna mark this thing that I just talked about, which is front wheel is free to roll. Okay, that's pretty much all I'm gonna write for the known. What should I write for my find? Okay, friction force, we'll just call that F. There's 2 other things it's asking for. Good. So I'll just make up variables for those. I'll call it normal front and normal rear. What do I do after known and find? Free body diagram. I'm going to try to start like harping on this a little bit more because once we get into kinetics, it becomes even more difficult to kind of look at a problem and know where to start. So the first 3 steps for every problem are exactly the same. Known, find, free body diagram. And then very shortly after that, you should be thinking about what equations of motion, right? Should I summon X, summon Y, moments? Those are like the first 3.5, 4 steps, always. And a lot of times that helps people get past this panic of like, I don't know what to do first. Okay, so my free body diagram, I'm gonna draw the slope, but I'm gonna draw it as a dotted line because it doesn't actually need to be drawn. Oh, yeah, thank you. Please keep doing that. Okay, and then I'm gonna do my best at terrible motorcycle outline. You get the gist.
I think I should go with two circles. I'm good at that.
That works too. A block with 2 circles is also sufficient. I also like to add any distances to this. So it's showing us here that from one wheel contact point to G, it's 0.5 meters. And from other wheel contact point to G, it's 0.7 meters. So I'm going to include that as well. Maybe draw that. And of course, it's not to scale, so I apologize. 0.5 meters, 0.7 meters. And then from G to the ground, it's 0.6 meters. And then here is 20 degrees, not 20 squared. There we go. All right, that's still not a free body diagram because I don't have any of my forces. So what forces do I need to add? Normal forces. Good. I'll do forces in green just to make them stand out. So this will be the normal at the rear wheel. This will be the normal at the front wheel. What else? Gravity, good. Gravity goes straight down vertical, and this is mass times acceleration, so 900 times 9.81. What else?
Friction.
Friction on the back wheel. Very good. Okay, so important things to note. Friction goes along the direction of the slope. The normal forces are perpendicular to the slope. And gravity goes straight vertical. Okay, this still isn't a fully complete free body diagram. What else do I need?
Coordinate system.
Coordinate system.
Oh, yeah.
Those are actually internal to the system. So you can think about the motor as turning electrical potential energy, or even like if you want to think about the battery as chemical potential energy. Or if it's probably a combustion engine, so chemical potential energy into motion energy. But that engine applies one torque to the wheel and the opposite torque to the body of the motorcycle. So all of that is actually internal to the system. So there's no external.
There's no anything.
Yep. Yeah.
I assume the direction of friction force wrong. Would I get a negative number?
Should be, yeah.
Does the direction of friction force normally go?
Opposite the direction of motion. So if and only if you know the direction of motion, there's a correct way to write the friction force. If you don't know the direction of motion, you don't know.
Assuming it's going uphill to the trail.
It is going uphill. In fact, friction is the only force that is pushing this thing uphill, which
So
is,
isn't the friction force in the same direction as movement?
it is.
You just said it was.
The wheel is pushing this way.
Yeah,
It's
that's
pushing against the ground in this direction. So friction is preventing the wheel from slipping in that direction.
Oh.
It's preventing the wheel from slipping in that direction. It's right. You have to think specifically about the motion of the particles on the wheel, not the motion of the body as a bulk object. Does that make sense?
Yeah.
Which is really fascinating because now you can think about any bulk motion is just like when we're walking, all we're doing is modulating our friction force.
I think like tire dynamics or like tire like deformation. It's like really interesting.
I don't like deformable bodies.
Well,
They get terribly nonlinear really fast.
I don't guess I'm not doing. Just it's cool. The principle, like, yeah.
Okay. All right, let's move on so we get to the end of this problem. All right. I did my known, I did my find, I did my free body diagram. I told you what should be your next thought in your brain. What should be the next thought in your brain? Equations of motion. Okay, so just to
Did you remember to write the coordinate system?
no, I didn't. Thank you, Samuel. Why am I choosing a tilted coordinate system?
It makes more things easier to solve.
Right. So to be a little bit more specific, there are three forces that perfectly align with a single coordinate direction. There's only one force that doesn't. So there's only one force that I have to split up using trig. Instead of three forces I have to split using trig and one that I don't. Yes, ma'am. Thank you. Okay, so the equations of motion that we have are, of course, sum of forces in the x, sum of forces in the y, and sum of moments about g. So let's maybe pick any one of these and see what it does for us. Sure, let's start with y. So let's do the sum of forces in the y direction equals what?
Am I right by starting at Y, or is there like a right answer or a wrong answer?
Not a right or wrong.
N, R, and F. And
Wait. Tell me the half of this MAY.
Okay.
Yeah. Don't go statics on me and forget that we have accelerations. MAGY. Now tell me, is this motorcycle going to accelerate in the y direction?
No.
Is it going to pop off the ground? No, not unless something terrible happens. Okay, so we're going to say this is 0. Okay, so it is actually static in the y direction, only in the y direction. Okay, so the forces that I have in the y direction are NR plus NF. Oh goodness, we have to do trig for this mass and weight. So what I'm going to do is draw my two coordinate systems, the one that aligns with my mass and the one that I prefer to use. Now, on the wedges of these two coordinate systems, that is an awful noise. Which of these wedges represents the slope that the motorcycle is on? X is just a single direction. I need it
Oh, from like flat.
flat to positive X, right? If you look at it, you squint your eyes just a little bit, this looks like this, right? So this is where we put that 20 degrees. And then every other wedge is the same angle. So this wedge will be 20 degrees. This wedge will be 20 degrees. This wedge is 20 degrees. Okay. So then I want to draw the right triangle for my trig. So my right triangle needs to have legs that are parallel with the coordinate system I want to move to, so the tilted X and Y. And it looks to me like this side goes down and this side goes down. Okay, so what part of this MG goes in the Y direction? You sure about that?
That's the X direction. Oh, wait, oh, it's the X direction.
Cosine 20 is the line.
MG cosine 20, and is it positive or negative Y? Negative. So I say minus MG cosine 20.
Could you also flip it and do 70 degrees from the x-axis?
Yes. Yep. Which makes it harder for me to grade. But it's okay. That's fine. It's okay. It doesn't matter. I can figure it out. I always know that sine of one angle is cosine of the other angle.
It's easier to know that I'm going uphill.
Sure. Okay, any other forces in the y direction? Nope, not that I see. Equals mass. What's my mass? Oh, acceleration 0. Everything on the right hand side is 0. Only in the y direction. Yes. Okay, how many unknowns do I have? 2. That's not great. I only have one equation so far. But I know that I'm an engineer and I can solve systems of equations, so I'm not going to freak out. I'm going to pause and try another equation of motion. What else should I do?
I would do X.
Okay, let's do x. Sum of forces in the x direction equals m ag. Yes, ma'am. Can I turn this agx into 0? Nope. Is it given to me in the problem? It is indeed. Yes. It's given to me in the problem as 3 meters per second squared. Okay, and then what forces do I have in the x direction? Gravity and friction. Very good. All of friction goes in the x direction, so we'll go ahead and say friction. And then gravity, back to our trig image here. Looks like the x arrow goes in the negative x direction. And then which trig sign is it? Sine 20. So minus mg sine 20 equals m times acceleration. Ooh, how many unknowns do I have here? One. One equation, one unknown. I can solve for f. Ruh-roh.
Could you solve for the normal? Never mind. I'm sure.
Oh wait, it's a plus, it's corrected.
Got it? Okay. All right. I still look a little screwed. What's next? Moments. Yay. Sum of moments about point G equals I G alpha. Tell me about alpha.
0,
Why?
because it's not rotating. It's like, it's rested, has 2 points resting on a flat plane, so it's not rotating.
Unless you start doing a wheelie,
Yes,
it's not rotating. Yes.
yes, but
And in fact, if you look in the book and you find this problem in the book, the one after asks you to analyze what happens if it starts to do a wheelie. But for this one, we'll assume it's not going to do a wheelie. It's going to stay in contact with the ground at both contact points. So yes, alpha goes to 0.
So it's summing
Sum of moments about G equals 0.
Yeah.
Yes. Okay, let's sum moments about G. What all causes a moment? What doesn't cause a moment?
gravity doesn't, everything else does.
Gravity does not. Friction and the 2 normals do. Okay, so just to save me from scrolling, I'm gonna copy this. Okay. All right, so the way we've drawn X and Y, Z, positive Z is out of the page, which tells us that this direction is a positive moment, okay? Z sets that direction. All right, which force do you want to deal with first? Friction, okay. So what's the moment caused by friction?
5.716 times 10 to the third newtons times 0.6 meters.
And then positive or negative?
Positive.
Very good. So F, which is 5719.7 times the moment arm 0.6, and it's positive. Good.
Plus n, the normal from the front wheel times 0.7 meters.
Positive or negative? Positive.
Plus n times 0.7.
Very good.
NR plus 4 times 0.5.
Very good. These all sum to 0. Okay. Now is the beautiful thing where I have two equations with two unknowns. One equation is here. Unknowns are NR and NF. One equation is here. Unknowns are NR and NF. Okay, so what I did is I went to the sum of forces and then the Y equation, and I solved for NR. R equals that. And then I plugged in that expression down in the second equation. Okay, so I got 5719.7 times 0.6. Give me 1 second because I have to see it
Oh,
to plug it in.
Could you not have also solved this by taking the moment about the normal forces or like where they are, and just including like the center of gravity, like G, in um your moment sum of moments, because they all equal 0?
I think that would have been okay. I think it would have been okay, but only because the moments sum to 0.
Okay,
So remember in
gotcha. So
class,
I should get used to this way of doing it, right?
you really should get used to defaulting to summing about point G.
Okay, thank you.
Because if alpha is non-zero, you have to sum about point G. unless you use that other equation that I showed you, but more often than not, it's kind of ish not worth it. I would rather you default to something about G so that you get it right, even if you never understand that second equation that I showed.
Gotcha. Thank you.
Yep. Questions?
Was how to get that moment of inertia of the half cylinder and the like final, not like the just the equation for the homework on the question 4.
Yeah, I can show
I'm
that.
worried I would get that. I would find like a wrong one on online.
Yeah.
Thank you.
Okay, so let's pretend I have a cylinder made up of 2 half cylinders. And from our equations, if I go grab it real quick.
So if I were to get 600, you were to get 597.5, would those both be counted as correct on the exam? Like, what is your like percent error?
Only sig figs should be rounded.
I hate sig figs. I try to tell everyone to keep around two. I want you to be correct to 2 decimal places. But in all actuality, I grade a lot more leniently than that. So if it's within a rounding error, I usually don't count it wrong.
So if I were to write 600, the answer is 597, but you're counting it off.
That's a whole 3 newtons. That's a bit
So yeah,
much.
that's a, like that's.
I would take like 1 point off and say there's a maybe egregious rounding error.
That's good. Wonder where I can get rid of that.
Okay, all right, back to this. So let's say we want to know, or let's say this is point G for the cylinder, and maybe this is, sorry, the semi-cylinder. I need to be more careful. This is point G for the semi-cylinder, and this is the G for the whole cylinder. And we want to know what is the mass moment of inertia about the axis that goes through G of the semi-cylinder. I just looked up online, the center of mass for a half cylinder is like some like 4r over 3 pi distance from the long side. I just got that from the internet. And then you say, okay, well, I know what is the total mass moment of inertia for the full cylinder about GC, because that's this one. So I would say that IGC for the whole cylinder is equal to I about GC for the semi-cylinder times 2, because there's 2 of them. Okay, but to find the mass moment of inertia of the semi-cylinder about this GC axis in the very middle, that'll take parallel axis theorem. So I end up with IGC, which we can get from here, the equation sheet, equals 2 times IGSC plus M semi-cylinder R between GSC and GC squared. Sorry, yes. Okay, so this is known from the equation sheet. This is what I want to find. This is given in the problem. And this is what I got online as 4r over 3 pi, where r is the radius of the cylinder. Yes.
I think it'd be the radius of the cylinder.
Yes. Okay, so known, known, known. I just solved for this. That gives me the mass moment of inertia of the semi-cylinder about its own center of mass.
Is there like an equation that we can memorize?
So what would the formula for the semi-cylinder, IG semi-cylinder be? Is it still the 1/2 mr squared? No, wait,
No, that goes right here.
right. Oh, I see,
I-
and then you would, okay,
I don't have it memorized.
So
I understand now. Thank you.
What?
ASC in this case, it like when you're solving for everything else, we just like a singular value, so it's not like an equation.
This one?
Yeah.
I mean, if you left all of these masses and radii as unknowns,
It's all for it, but that's.
yeah, but you can just plug in numbers. But notice that I for the full cylinder, or sorry, the mass for the full cylinder is going to equal 2 times the semi-cylinder mass.
This is for question 4, right?
Whichever is the very last one. I forget how many I gave you.
Is it on, is cylinder on the formula sheet? Cause I didn't see it.
It's this.
Yeah.
It's a circle. Right? Like on the formula sheet.
Well, no, you only use.
Yeah, okay, so that's because I pulled out only those that were necessary for the last final exam on the equation sheet. So in the meantime, feel free to use the Hibbler books full cover sheet or just Google it. Okay, does that make sense? So that I agree, that was tricky. That was a little bit mean. Okay, any other questions? Oh, I wanted to add a comment for these kinetics problems. I would still consider what we just did as a fairly straightforward problem. We've basically left in all of the kinetics problems that we've done so far, the accelerations have been quite simple, right? So like the acceleration in the y direction went to 0. The acceleration in the x direction was given and it was constant. The acceleration, the angular acceleration went to 0. So the accelerations have all been very, very simple. The way that we step up these problems in difficulty is to add back in all of our kinematics knowledge. So we start to talk about a rigid body that's moving along a curved path with a known the path is given to us as like r as a function of theta, and so we have to start thinking about these other coordinate systems and incorporating what we know about those coordinate systems into our definition of the accelerations. So what we plug in for accelerations on the right hand side, that will become more complicated. And so I've been focused so far on just kind of belaboring the sums of forces and sum of moments side of this equation. But in reality, we need to make sure that we can handle both sides simultaneously. Make sense? Okay, any questions online? All right, we're over time, so I'm gonna stop us here.
Wait, could you scroll down to the solution really quick though?
Yep,
All right, thank you.
all good?
Thank you, Dr. Higgins.
Thank you. See you guys Thursday. Bye.